So we have taken this example number one. We have given a footing, and the footing size is determined, which means there is no soil design or no sizing of the footing as in terms of length and width. And the question here is about the reinforcing. Ultimate force was given to us, which is the ultimate column load that's supported by the footing. It says here 680. We have also the strength of the concrete 3000 psi, and we have 4 different reinforcing, you can say here, programs or patterns. And you'd like to see which one is most likely to be the right one. We draw this footing in plan, and then we show the column right in the middle. Then we have drawn it as an elevation, and then we showed here the ultimate pressure, the underside of the footing. If this footing, if you push down the entire footing with the column, there's going to be some reaction from the soil, and this reaction is going to be causing bending on this cantilever part of the foundation. And it's going to happen in both sides of the column. So you're going to have here one critical section, another critical section here for the moment. And the moment that you're going to be taking is going to be at the face of support. You don't really need to go to the center of support to maximize the length of the cantilever. This is simply because the depth of the footing in this case is going to be including the column. So you have full resistance, you're right on top of the support. So for the moment or for the picture check or design, we're going to be taking the critical section at face of support, which means at distance x from the edge of the cantilever. We have here some calculation for x. Since this column is going to be right in the middle of the footing, you can take 8.5, subtract 2 feet, divide by 2 to get the cantilever length. We're able to find out here the moment by finding out the total force acting on this cantilever section. It's going to be right in the middle. It's going to be equal to the ultimate pressure, Q ultimate, multiplied by this x, multiplied by this b, 8.5 feet. And then you come back again, multiply by x over 2, because it's going to be the moment R. Same thing here, we could have done it along this critical section. You can end up with exactly the same moment. The reason is this cantilever length is going to be the same in both directions, because you have here rectangular, you have a square footing, and also you have a square column. So the cantilever length in both directions would be the same. Direction meaning, and let's say in the x and also in the y direction is going to be the same. When we tried here to pick the depth here was kind of tricky to us, because you understand that the reinforcing bars, you're going to have it in 2 layers. So the depth for each direction is going to be different. But because I'd like to do here quick analysis and estimate for the reinforcing bars needed, I'm just going to take here somewhere in the middle between the 2 depths. So I'm going to say 30 inch, which is the total thickness of the footing. You subtract 3 inch for the cover, and then you subtract, let's say, an inch. Some people just take maybe 5 inch total. So in many cases, you see people just saying 30 inches minus 5 inch is going to be 25 inches. Just take the depth 25 inch and continue for your first estimate of the reinforcing bars. To do this estimate, what you need to do is set the demand is going to be equal to the capacity. Your demand is going to be M sub U that you just calculate out here. You say worst case when it's going to be equal to the capacity, phi man. Now you take it from there. You say if this is here is going to be equal to M sub U. Now looking for AS, and of course you have here phi factor times Fy, and then you have D minus A over 2. You don't have A over 2, so you can estimate D minus A over 2 to be maybe 80% of D, maybe to 95% of D. Any estimate is going to be okay, because at the end, you're going to be back checking your answers here. You need to back check and be sure that you have enough phi man more than M sub U. You don't just do it this way. This is like a quick estimate for the amount of reinforcing bars again. Here in this problem, I said it's going to be maybe 90% of D. If you say 80% is okay, if you say 92% or 93%, it's going to be okay. Now, so the AS required is 4 square inches. We're going to provide here 10 number 7 based on this given choices. So I decided here to go with 10 number 7. Someone else could have maybe tried first 10 number 6 and see if it's going to work. Most likely this is not going to work, but you can try that if you want to. And then you find out AS, you find out A, compression block depth, and of course you need to find out C and epsilon S, and of course you need to find out phi factor, which turned to be here 0.9. So I don't want you to think that, okay, I have showed here this problem without determination of C and strain in the steel and the phi factor. That's not needed. It's still needed, right? So I want to be sure that you guys understand that. The reason that I didn't show it here because I have repeated a few times for you guys. So there is no need to repeat it again. But you need to understand when you do concrete section analysis, when you do phi man, you need to be detailed the way that you have learned first time. So I'm gonna put here phi as part of the things that you need to determine here. Say you need to find this, also find phi factor based on these two values. So what happened here, we find out that phi man is gonna be more than m sub u, which is very good. Now I guess we can check the shear. And this is a kind of general rule. Please remember this because I've seen here that some people do not know it yet. That when you do here critical section for shear, when you do shear analysis, you cannot take the shear as to be the total force. So someone's going to say, here's total force, 680, which is this number here, this 680 kips, divide by 2 because one half of the force is going to be going to the right, other half is going to be going to the left, and this is incorrect. Very similar to beams. Critical section for shear, it's not going to be at the face of support. It is going to be at the distance from face of support. So in our case, like in this elevation, here is face of support. I need to go the distance with this 45-degree, which means the distance from here to there is going to be about 26 inch. So I said, okay, this is going to be here D, which is 26 inch. You divide by 12 to put it in feet, and you should be able now to figure out your X distance. This used to be 3¼ feet, right? So you reduce it by 26 divided by 12, you end up with 1.08 feet, which is going to be this X distance. Now you should be able to find out the shear. The shear is going to be the total force that's trying to lift this piece up. This is equals to Q ultimate, the same Q ultimate that you calculate out. You multiply by this X, multiply by 8.5 feet. You have here 86 kips. Now you need to find the strength, the capacity. How the capacity is done, you say there is no reinforcing here to take the shear. It's true that I have reinforcing at the bottom, but this reinforcing for flexure for the moment. There is no ties. I didn't add here any ties. So in this case, I'm going to have only the concrete strength, and I can simply do it based on this equation. Strength of concrete was given at the beginning of the problem. You have the depth, 26 inch. You have the total width, because this is going to be here the cross-section area of the concrete that's exposed to shear is going to be equal to the width applied by the depth. Times, of course, phi factor of 0.75. So I'm good with this shear check. So flexure check is good. Shear check was very good. The third check that you need to do for foundation is going to be the punching shear. This is a part that we stopped at last time. So this punching shear, it is really about when the column itself is not going to be like big in size. I'm talking about cross-section area of the column. And the concrete footing or the slab is kind of thin. When it's really thin, you don't want this column to be just running through the slab or through the footing, if you like. So in this plan here, I'm showing you a few columns on a concrete slab. So this here, you can consider this to be a concrete slab. This is not really about footings only. This punching shear, again, is going to be for slab and for beam and for footings. So here a few columns. The spacing in the X direction, we're going to be called here L1. The spacing in the Y direction is going to be called L2. Tributary area is going to be given by this dash lines, right? Which is going to be, let's say, L1 multiplied by L2. So tributary area here is going to be L1 by L2. So if you want to find out the amount of load that goes to this column, you just can take L1 times L2 times the uniform load that you use in your design. That'd be ultimate, whatever load that you have. This is why you have this dash line. Now this column here, it is trying to penetrate this concrete slab or the footing. So when this penetration happens, it doesn't happen at the face of the column, at face of support. It happens at slightly a distance away from the face of the column. When you look here at these pictures, for example, you see here that the failure didn't happen at the face of the column. You still have a piece that sticks of the slab that sticks with the column. Same thing here. Look at all of these columns. They have a piece of this concrete slab. Same thing here. This means critical section for punching shear doesn't happen at face of the column. It happens at a different section. Same thing here. Where is the critical section for shear? I cannot say that the cracks happen right at the face of the column. It happens a little bit further away from it. Also, based on this testing, look what happened. The cracks, location of the cracks. The crack is coming this way. So I'm going to say critical section. I'm going to assume it to be right here, somewhere right here. This distance here is usually taken as d over 2. We'll say the distance from here to there, right, is roughly, I'm going to write it down here. It's going to be roughly d over 2. So actually, you're going to have it from both sides, and you're going to have this perimeter of the column at d over 2 distance is going to be exposed to this punching shear. Here's the column in plan, and here's going to be the shear section, the critical section for shear. And look where it happens at d over 2 from each side. So I'm going to have a perimeter here of this sheared area times the slab thickness. So just imagine this here a plan view, here's the elevation. This column is pushing down with some given force, right? It wants to penetrate through this footing or through the slab, whatever that you have, whichever that you have. Now, if you take here, this is going to be the critical section for shear. It means the sheared area or area of concrete exposed to shear is going to be equal to this perimeter applied by the thickness or this depth, if you like. So now I have these two new terms, bx and by. And now what's bx and by? Bx and by is going to be the dimensions of the critical section of shear. Bx equals cx, the column length in the x direction, plus d. Why? Because you have d over 2 here, d over 2 here. Remember, in one-way shear, we didn't take it at d over 2. We have taken it as d. So there's some differences here. When you have two-way shear or punching shear, you take the critical section of shear, is going to be at d over 2 distance from the face of support. When you do one-way shear, what is a one-way shear? Just to remind the people, remind myself, one-way shear, when you just take it about one direction like this, you are checking here whether the thickness and when this uplift that's coming by the footing and the soil pressure is not going to be cutting or breaking or failing this footing here in shear in one-way shear. So two-way shear is going to be different from one-way shear. So now, how much is this bx? I'm going to say bx equals the column dimension in the x direction. We call it column. C stands for column in the x direction. So bx equal to cx plus d, because you have here d over 2, d over 2. Same thing for the y direction. by is going to be equal to cy plus d over 2 plus d over 2. So it's going to be plus d. So I'm good with these two dimensions. Now, what is this b sub 0? B sub 0 is going to be the perimeter. The perimeter is going to be equal to times bx plus by. Or you can say bx plus by plus another bx plus another by. With that, you have the perimeter. Again, the area exposed to concrete shear is going to be equal to this perimeter, b sub 0, multiplied by the depth, which is from here to there, times the perimeter. Now, how much is the shear stress that you need to check against? I'm going to say now, in this case, the shear demand as a stress is going to be equal to the vertical load. I'm going to call it here V sub U, which is the same as P sub U for columns. I'm going to say here, P sub U is going to be equal to V sub U. Let's give it the same thing, which is a column load, actually. You divide it by this AC, by this perimeter times the depth, by the sheared area. With that, you get V lowercase. So look at this. This is going to be V uppercase, which is a force. This V lowercase is going to be stress. Say this is your force. And this V lowercase is a stress. Stress meaning what? Like PSI, you're going to see here, could be KSI or PSI. Two units that you'd like to work with. But I would prefer just to leave it as in KSI. Any questions on the punching shear? Yes? We're good?
No, Professor. Would you be able to explain a little bit more the critical section? Because you mentioned that there's a perimeter. I'm just trying to understand it.
Okay. Give me a second. Give me just a second. This is a famous picture that I'm going to show you now for the punch and shear. Look at this picture. Okay, you see this picture?
Yes.
So here's expected failure. You're going to have lots of pressure on the concrete slab. Same thing, you can look at it if you just put it upside down, and you can consider this to be your footing, and the pressure is going to be pushing the slab down or pushing it up. It depends on the direction of load. Now, the section that here you're looking at is the sheared area, which is the same as this area here, right? It's going to be the surface area of the concrete. You can see, how much is this equal to? How can I figure it out? Would the shear happen or the failure happen at the face of the column? I'm going to say no, because I have here a piece of concrete that sticks out. You see this piece of the slab? It comes with the column. So the critical section for shear, for this punching shear, doesn't happen at face of support. And this area here exposed to shear is going to be equal to the slab depth multiplied by the perimeter. Do you agree on this? Is this clear to everyone?
Yeah, that
Okay.
makes sense.
Okay. This makes sense because it's going to be the sheared area. So if you know the amount of shear force causing this sheared area, right, or acting with this sheared area, you take this force, I'm going to call it here P sub U or V sub U, divided by this sheared area. I'm going to call it here AC. This AC is going to be equal to the perimeter multiplied by the depth. Let me put this back. All right, here is the shear stress. It's going to be equal to V sub U divided by the sheared area. Sheared area is going to be equal to the perimeter. This is going to be the perimeter multiplied by the depth, right? Which I was just looking here at. Perimeter multiplied by the depth. Perimeter is called here B sub 0. Where this coming from? I'm going to say it's coming from 2 times bx plus by. So the question is, how would you come up with this bx or by, right? This dimension. You say this is simply, you just take it from this figure. You just take here's the column dimension. You add 1 full d to it. So for example, the depth of the slab is, let's say, 10 inches. So you take the column dimension, let's say 20 inches or maybe 24 inches, you add 10 inches to it in both directions. Are you good, Alex?
Yes, that makes a lot more sense.
Any other questions?
Yeah, are the D values in both figures the same value?
Yeah, you can take it as an average value. Yes, it's giving the same value.
I don't understand how you relate P sub U and V sub U to be equal.
They're not equal. This is going to be V lowercase and this is going to be V uppercase.
No, P sub U and V sub U. The demand.
What?
P sub U.
P sub U usually, okay, let me tell you why they are equal to each other. When we do column design and column analysis, we call the axial load to be P sub U. So I'm going to say here, column axial load, column axial load. We usually refer to it as P sub U. You know that, right?
Yes.
Now, this same column axial load is going to be the same as the shear force causing this punching shear. So it just happened that it's going to be the same force. So when you do column design, you call it P sub U. When you do punch and shake, you call it V sub U. But actually, it's going to be the same force.
Okay, got it. Thank
All
you.
right. Very good. Thank you. Now, I have here the demand. So you see here, with that, I was able to find out the demand. And the demand in this case was not equals to some kips. So I'm going to say here force in kips, right? My demand at the end, this is what I'd like to see as a stress. So what I'm going to be checking here is going to be stress versus allowable stress, not allowable stress. Let's say here, limited stress, capacity stress. So here's going to be PVC, and you see this is here lowercase, am I correct? As a stress. So okay, this is going to be stress. And it's going to be equal to the phi factor, as we know phi factor for shear. We're going to still keeping it as 0.75. There's no change in this. Multiply by something that we call here shear factor. This shear factor in one-way shear, do you guys remember what value did we use for one-way shear? Yes? How much was the shear factor? In one-way shear, did we do shear factor or we didn't? I'm just wondering.
I'm trying to remember. I think it was like 0.8, right?
Is it
Here's the
0.8?
one-way shear. Just for you guys to remember what we were talking about. And here's the concrete strength. I'm going to take you to the slide that says concrete strength. How much was the shear factor? 2, right? So the equation says 2 square root of V prime C is going to be the stress. Multiplied by some cross-section area, it's going to get you a force. This is going to be V uppercase, correct? So if I did not use the cross-section area exposed to shear, it's going to be stress. Therefore, this value here, 2 square root of V prime C, is going to be like the stress, VC lowercase, okay? So in one-way shear, the shear factor is equal to, this is not safety factor, this is shear factor equals to 2.0. Let me call it here. Okay, so in here, it's not going to be equal to 2. It's going to be larger than 2. And here's the reason. This shear factor, it says, going to be the minimum or the minimum of the following, right? And here it says 2 plus, 2 plus. So it's going to be higher than 2. Right? Now you have two-way shear. Resistance is going to be higher than that for the one-way shear. And here's the reason. In the same time that the slab is pushing like this on the column, you have this pushing down from both sides. So the concrete here gets stronger because you have more confinement. In one-way shear, you're just trying to cut it down this way. This is what you do here to the concrete. There is no any other action from the other side. And here you have the action coming from the X direction and Y direction. You see, look at this. You have here a point load that pushes this down from here, and then you have from here. This would give you here just one-way shear action, correct? But once you start to push down from this point and also from this point, now what are you doing to the slab? You are bending it in two directions. And for that, the slab would get stronger in shear resistance. And this here, this is a reason that the code recognizes this issue and gives you that the shear factor is going to be equal to 2 plus additional factor, 2 plus additional factor. And then at the end, they say the maximum value is going to be equal to 4. So you simply can take this shear factor from 2 for the case of one way, right, to a value of 4 in two-way shear or in punching shear. Now let's see here the factors that you're talking about. I mean, it's just simple factors. It's not really complicated. I'm gonna say, what is this alpha S divided by beta sub 0, or 4 divided by beta sub C? So beta sub C is gonna be the aspect ratio of the column. You take the long column dimension divided by the short column dimension. For example, the column size, this is just an example, right? Right? If the column size is 24 by 12 inch, how much is this beta sub c? I'm gonna say here beta c equals how much?
2.
2.
2. It's gonna be equal to 2. It's gonna be that simple, right? I said, okay, good. So in this case, I'm gonna be taking this shear factor is gonna be equal to 2 plus 4 divided by 2 equals, and in this case, shear factor equals to how much?
4.
Is gonna be equal to 4. It's gonna be that simple, right? How about if the column square? What shear factor would you get? Shear factor sub c. How much this would be if the column square?
4.
If the column square
6.
is gonna be equal to 6. But you have a maximum value here of 4, right? So it's true that you're gonna be getting based on this shear factor sub c is gonna be equal to 6, but at the end, your shear factor, that's the usable one, is gonna be only 4. All right, so what is this alpha sub s? They say this alpha sub s, it depends on the column, right? If you have interior column, what's interior column? You'll see this is giving interior column here, right? If you have interior column, your factor alpha s is gonna be equal to 40. If you have edge column, 30. If you have corner column, it's gonna be 20. Let me show you here this picture that shows a failure, some failure. I'm gonna say here the column here at this edge. You see this? This is gonna be an edge column. This is not a corner column. But this column is kind of interior. But if the slab just happened here at the face of the column, very close from here, I would call this a corner column. So this here may be a corner column. It's given an edge column. It's given interior column. And for each one of them, you have different value for alpha sub s. 40, 30, 20. You can say, how about when I have the footing that we were talking about maybe 15 minutes ago? What happened to it? I'm going to go back here for quick. Is this interior column, edge column, or corner column? How do you consider it? Hello? Is this column here at the edge or at corner? I'm going to call it interior column. So in foundation, when you have a situation like this, you take alpha s equals how much? 40, because the column here is going to be called interior column. All right, let's see the example. So I'm going to be taking the same column that we just designed the footing for. Same 8.6 by 8.6 by 2.6. You have 24 by 24 inch, 3,000 psi concrete. Ultimate load on the column is going to be 680 kips. Now, this one here, this is the one that I called it a minute ago. I called it P sub U, which is also equals to V sub U for punching shear, right? It's going to be the same one. Now it says here, which of the following statements is correct? Because now I need to think about the options. The footing is safe against punching shear. So you did punching shear, everything is good. It's going to be option A. Option B, it says, to make the punching shear safe, as if you have tried your analysis and turned to be unsafe, the specified concrete strength needs to be a minimum of 3,500 psi. So in this case, you're asking here in item B, change the strength to 3,500 psi and back check the punching shear. Or you can make it maybe a minimum of 3 feet. The total thickness is going to be a minimum of 3 feet, which means increase the thickness and keep the strength of the concrete to be the same. Or you make it 4 feet. Okay. Anyways, this is here to complete the problem that we started. So with this footing size, and this given load, at the beginning we did the flexure design, and then we did one-way shear, and then we are doing here two-way shear, which is a punching shear. The third item for the trench design. So, okay, here's the analysis that I need to do. The depth, how much is the depth of the footing? We said, well, in this case, I may take it to the bottom point, to the bottom rebars. I'm going to be taking it 26.5 inches. All right, it's fine. If you decide here to make it 26 inch, this is fine, but this is like a little bit more detailed analysis. About Bx and By, the critical section for shear. We said we're going to stay at d/2 distance from the face of the column. So your column size 24, and the depth, you add 1d to it, it's going to be 26.5. Here we go. Here's Bx, here's By, is going to be the same. Perimeter, 50.5 times 4. Multiplied it by the depth, 26.5, and this is what you get. 53 square inches. Now this is going to be the shear area. The shear stress is going to be equal to the column axial load, which is the same as the shear force on this. Punching shear, 680, you divide this by the sheared area, and with that you get, let's say, 0.127 psi, which is 127 psi. So I'm going to say same as 127 psi. All right. Is this a demand or the capacity? Just for curiosity here, just to confirm with you guys. Demand or capacity? Adolfo, are you there? Adolfo?
Yeah.
Is this a demand or capacity?
Would it be the demand?
Are you asking or answering? Just
Or
want to...
it's answering.
Okay, if you're
What's-
asking, I can help and answer. But you're answering, right?
Yeah.
Okay, so this is a demand.
Mhm.
Okay, did I do the capacity yet for this example or I did not?
It's based on the ultimate load, so not yet.
So not yet. Okay, thank you, Adolfo. Thank you very much. So now I have here, this is going to be the ultimate stress, which is the demand. Now I need to see the capacity. As I said here, capacity is going to be given by this slide. So you have just one slide here for the capacity that you can look at. It's going to be so simple. So I said here, okay, alpha S is going to be equal to 40. Why? Because I have interior column. Okay. Beta sub C, long divided by short column dimension, is going to be equal to 1.0. How about beta sub 0, which is the perimeter divided by the depth, 762. Now let's do the factor C, factor sub 0, and the maximum factor. So this is going to be the same like the one we did for the column, the quick one when I say when you have a square column and turn to be 6. And then based on the perimeter, the other beta is going to be 7.25. Your maximum value to use is going to be 4. Now which value to use? I say, let me here use this max value because this is going to be my limit. They say do not go beyond 4. If you are getting higher value than 4, don't take them. So my max here, the one that controlled for the shear factor, is going to be equal to 4.0. And where is shear strength? You can see shear strength is going to be equal to phi times 4 square root of a prime c. Now here we go. 4 square root of prime c, 219 multiplied by 0.75, 164. How much was the demand? If you go here back one step, anyone remembers? You say the demand was equal to 127 psi. So good.
Did you say alpha was interior? Alpha S?
Alpha S? Yeah,
First
because
line.
this column is interior.
Okay. Thanks.
How do I know it's interior? Let me look at the picture. Is this interior column or this is an edge column or corner column? I'm going to say, well, I cannot judge it this way. Let me look at the big footing, like in a plan view. So, all right, let's look here. Is this here a corner column? So I'm not sure. What does mean by corner column? If you put this column here, it's called a corner column, right? If you put it here, you call it edge column. This is not a corner column, right? This is not an edge column, so I'm going to call this to be interior column.
Thank
So
you.
I guess here, no problem. I guess here definition of interior column versus edge column versus corner column is clear to everyone. Any questions from anyone about this definition? Okay.
Professor, going back to
Yes.
the other problem, so the ultimate shear stress, that wouldn't be the maximum capacity? I think I misunderstood
The
that.
ultimate? The
Yes.
ultimate is a demand. Usually once you see here V sub U, this is the demand, right? P sub U is the demand,
Mhm.
right?
So then the 0.1 127. That's the demand, right?
Let me show you this. This is from slide set number 3. What is this? This give you slide 16. You can take a note of it. It says here VPN is going to be more than P sub U. What is P sub U? Demand. What is V sub U? Demand, right? This is going to be based on what? Based on this load combinations, right? What is VPN? The trends. So the ultimate is the maximum value that you apply on the structure member, if you like. So anyways, did I answer your question or
yeah,
not?
that answered my question. Thank you.
Okay. So we did here a check on the shear, it turned to be safe, everything is good. So now I showed you a quick example here without going into lots of other details related to foundation design, that when you are given here a footing and you have the ultimate load, you have the concrete strength, and then you have been asked here to check the strength of the concrete footing itself as a structure member. Now I didn't do here the soil design, the soil design by sizing the footing, like based on the ASD that we discussed last time. This is not included here in the 3 examples. The 3 examples, I give you a footing, the size is done, we're done with it, and I'm trying here to check the trends of it. So I'm gonna have here 3 checks. First one is gonna be for the flexure for the reinforcing. Second one is gonna be for the one-way shear. Third one is gonna be for the puncture shear. So when you have a footing, this is gonna be the 3 checks that you need to do. Okay? All right. Now let's go here to the following slide set. This is gonna be also about foundation. We're gonna continue on foundation. Now, we need to think about the sizing of the footing. This is a thing that I just went through it quick last time. At the beginning, I said when you size the footing here, you need to work with the surface loads, and you need to use here the ASD design. So we're trying here to find out this size, like this 8.6 by 8.6, the one that we used, or maybe 5 feet by 5 feet. The area required here, which area is this? I'm gonna call this to be the contact area. Between what? So you can say this give you the contact area, right? This area required is give you the contact area. Between what? The footing and the soil. You guys with me? Like in plan view, when I was looking at the footing, this gave you the contact area between it, right? You'd like to keep the soil pressure within certain value. This value is gonna be called here bearing capacity. So I guess you guys, I've showed you here last time, a SOS report that shows the allowed bearing capacity. So this BC is gonna be equal also to QL level. In many cases, you find it written this way in soil analysis book. And this is gonna be given to you by the soil engineer, which is the same as geotechnical engineer. So this contact area needed is going to be equal to the service demand. What's the service demand? You just take the dead load plus the life load. You just do it according to the ASD load combinations, not to the LRFD. So in this case, I don't have 1.2 dead plus 1.6 life. I don't have 1.4 times dead load. I don't have any of that. I just add them to each other. And this makes sense because look at this. You just take this force here, right? If you take the force, divide by the soil bearing pressure, it's going to get you the area. Makes sense. Because if you take this area, multiply by the pressure, okay, the total force applied on the footing, right? If you take this area, you multiply by Q, it's going to get you here the total force on the footing. So, okay. I have a quick example. This is so simple, I guess. It says the column dead load is this much, and the life load is going to be 560. A square spread footing is proposed to support the column. The soil bearing capacity is 7,000. And which size would you use? The most economical size. What does it mean by most economical? It means the smallest. Economy here is to save in concrete. You don't want to go to a very big footing. So I'm gonna say, here's the size available. It says here square footing, 15 by 15. Would that be the answer? Not sure. 12 by 17. Can you use 12 by 17? Yeah, say no without thinking, because this is non square. Maybe 18 by 18, but not 13 by 16. So I'm gonna have either 15 by 15 or 18 by 18. Okay, good. Let me do it for quick. Yes, say the total service load, B service demand, is gonna be what? Dead load plus, this is your dead load, right? And this guy here, yeah, say this guy here is gonna be plus life load. Is gonna be for this box, for this term. Total load 1410. Bearing capacity is how much? It says here 7,000 PSF. This number is giving kips. So the 7,000 means 7 KSF. So the same as 7,000 PSF. It's giving the same as 7 KSF, which is divided here by 1,000, a factor of 1,000. Now the area required is going to be 201.43 square feet. Can I do this? Can I just find the square root of this number here? Can someone help me and find out the square root of this? Yes?
Yes, 14.2.
14.2. So which footing should I use? Most economic, I'm getting here 14.2 is needed. I'm gonna provide here 15 by 15. I don't really need to go to 18 by 18. So it's gonna be 14.2 to the half, power of half, like square root, and then use here 15 by 15, and here is the amount of contact area that you provide. You provide now 225 instead of 201. So the actual soil pressure should be now less than 7, I guess, right? How much is the actual pressure below the footing? Can someone help me also with this? The actual pressure.
Is it the 1,410? Or
This is a force. The 1410, this is gonna be the force. Pressure Q.
1410 divided by 225.
Okay, very good. I'm gonna say here 1410 divided by 225. What's 225? The actual contact area. So when you're looking here for Q actual, like the actual pressure that you put below the footing, is gonna be equal to 6.26 KSF. Which makes sense. Now you provide more contact area, the pressure was lower than 7 KSF, which is the limit. So this is good. You can compare 6.26 to 7 in your analysis, or you can compare 201 to 225. You say, I provide more than needed, I'm good. Or you say, here's the actual pressure is gonna be 6.26 compared to 7, lower than the limit, I'm good. My design is okay. Questions? Or should I just proceed?
would you be able to go back? So the 225 represents what again?
It's right here. What is that?
The 15 by 50. Oh, okay. Makes sense. Sorry about that.
Yeah, that's fine. It's absolutely fine. Am I moving a little bit fast?
I think you're good. Thank you.
Okay. All right. All right. Now, this footing here was exposed to only axial load, right? This is all what we have, just an axial load on the footing. But not all footings are that lucky just to be exposed to only axial load. Footings usually, they are exposed to an axial load and some moment with it. So right on the top of the footing, right, you're gonna have an axial load and a moment on the same time. Now let's see how to handle this. This is gonna be for footing here, supporting loads and moments in the same time. I guess if you have a few forces acting on the structural member, you can just take each load separate and deal with it, and at the end, you can add all the effect, the final effect as a stress. I'm gonna show you how to do this. Let's say that for now, I have a load and a moment, like a point load, vertical load, and a moment. Due to the vertical load, the stress due to P is gonna be equal to the force P divided by the contact area E. But also when you have a moment, and let's say this moment is separate from this axial load, It's going to be a separate load case. The stress under the footing due to moment is going to be equal to the moment divided by S, M divided by S. I guess we have seen this before, right? When we were talking about cracked concrete or uncracked concrete, when the reinforcement was not included. You guys remember this equation or no? Yeah, no? Yes, no?
Yeah, cracking moment, yeah.
Yeah, it's right here.
Oh.
Older slide set, number 2, slide set number 8. Look at this. The stress equals M over S. That's for the concrete. Now, this gave it for the soil. Same equation, same concept. Nothing is different. You guys, you have studied normal stress. And the normal stress in mechanics of materials, you have combinations of axial load and moment. And you guys, you have seen this equation before. You combine here the axial load effect with the moment effect. Anyone recalls this or no? Or you have no real connection to it at all? Yes, I'd like to hear.
Is it from Moore circle?
This is even before Moore circle. Moore circle was a little bit advanced.
I think that's going to be on that.
Strengths and materials. No.
The strength of materials. Did you guys take it or no?
Yes.
Yes.
Yeah. So P over A. So what is it called? Strain.
The stress and the strain, normal stress, normal strain problem.
Mhm. Yeah.
What was the course number?
308.
301.
301.
301.
301.
302, no?
301. Shear stress, normal stress. Is it normal stress? Normal stress, average stress. Was there something called average stress? The 301. Beam bending.
The average stress, but shear is going to be 0, huh?
Combined loading. Was it called combined loading? Here we go. Here's the equation. This is from mechanics of materials, right? I'm just able to find it. Did you guys take this before or no?
Yes.
Yeah,
Yes.
this is what you studied. You have this axial stress and axial strain, and then you have due to flexure. Sigma max is going to be equal to M times C divided by I, and I divided by C is equal to S. This is what we call here section modulus, right? So we call this F sub P and M sub M. This gives you the stress coming from the axial load and the stress coming from the moment. And then we add them to each other. And then we say plus or minus. Why plus or minus? Because at one time, both of them is going to be compression. At the other time, one is going to be tension, one's going to be compression. So you subtract them from each other. Okay? So this one here we have taken. And look at this column here. Did you guys take this example before? I'm sure that you have taken it, right? And also we have taken it here in concrete. When we say that I have eccentricity of this much, you remember the eccentricity, the axial load, we say that this is going to be actually equal to axial load and a moment. So we have all of this in mechanics of materials, and we have some analysis for it. If you have homogeneous material, you guys have taken this before. All right. Let me go back here. So this is how you combine the stresses, right? You have a stress due to axial load, and you have a stress due to moment. You just combine them. We say here plus or minus. Definition of all of these terms. What does it mean by axial load, the P, the moment M, contact area, section modulus? How do you do it? Okay. The soil pressure due to vertical load, soil pressure due to moment, footing length, footing width. This is also that you need both of these two pieces of information to find out this. Here's the two load cases. I'm going to call this to be two separate load cases. One of them is going to be showing only axial load, the other one is going to be showing only moment. I call this one A, this is going to be one B. Right? Now I have here the pressure is going to be under the footing due to the vertical load. And we have done this already in our example, and we know how to use it. And design the footing for. Now I have another force here acting on it, M, and F sub M is going to be equal to M divided by S, the moment divided by the section modulus. All right, so I said now I need to combine them. Let me combine them here. This is going to be different from this analysis. I'll tell you the reason. You see this analysis? This analysis is great. It is good if you have like a steel section, right? If it's good if you have a wood section, some homogeneous section like this, it's going to be great. The problem when you have soil, soil cannot take tension. Do you guys know the soil can take tension? You can say no, soil cannot take tension. So just imagine if this gonna be here your footing, right? You see the picture? You see what I'm showing here, right? And here's the soil. Now once you start to apply load, this gonna be lifting up. So once it's lifted up, what's gonna happen? There is no now contact between the soil and between the concrete footing. So you cannot really do this. So here's the issue. You have two options when you run your analysis. And let me assume here for a second that positive would mean compression. And negative indicates here tension on the soil. If I try both of this F1 and F2, what does it mean by F1 and F2? I'm going to say it means two stresses at each end of the footing. It's going to be like this, F1 and F2. If I try the equation that you're just looking at, and I find out that both of these two stresses is going to be positive, which means the entire footing is exposed to compression, I'm going to say good. There is full contact between the footing and the soil. The problem here is going to happen when you have this moment effect on the stress. It's going to be much harder than the effect of the vertical load on the stress. The footing is going to start to lift from one side and there won't be any contact. But you know what? The soil cannot take tension, so you cannot really extend this. Soil cannot take tension. It's going to be almost similar to the concrete. You remember when we say concrete cannot take tension? So what's going to happen? Concrete is going to crack. Now in this case, there's not going to be any contact between the footing and the soil. And if you have a situation like this, it means that your equation that you started with is not good anymore for this case. The equation that we started with, which is this equation here, is good only if you have full contact between the footing and the soil. This is something that you usually teach in soil mechanics and foundation design and this kind of things. So I'm going to say here, I'm going to be running to here. I'm going to say FP and FM. What is FP? It's stress due to vertical load. FM, stress due to the moment. If FP in value is greater than FM, you shouldn't have a problem because you're going to end up with this distribution. So when you add them to each other, you're going to end up with F2. When you subtract them, you end up with this F1, which is going to be positive, and you're going to have compression and full contact between the footing and the soil. The problem here is going to happen if the numerical value of FM is going to be more than the numerical value of FP. What do I talk about? I'm talking about this one here. If you have lots of tension here, and then you think about this side of the footing, and this tension is going to be more than the downward, which means this compression stresses. So in this case, you're going to have an uplift. The entire footing here is going to be lifting up from the soil. There's not going to be any contact. I have it here summarized in this line. It says when FP is more than F sub M, everything is going to be good, and you can use this equation 4, which is this equation, right? But if FP is going to be smaller than F sub M, what's going to happen? You need to use these equations. I'm going to have here a new set of equations that I want you to use in this case. It defines here a new variable that you call X. X is going to be equal to the length of the footing, subtracting the E. What is E? Eccentricity. I'm going to show it to you in a second. Here's eccentricity. It's going to be equal to M over P. So when you have this vertical load, right, and you have M in the same time, you take M divided by P is going to get you the E eccentricity. Very similar to what we have done in the column design, if you guys recall this. And then the stress here is going to be equal to 2/3 of P divided by XB. And what is X? It's going to be equal to this term. Okay, let me see what's going to happen. So here is going to be the two separate cases, right? And this is going to be E because now we have M and P in the same time, meaning I can just take this load and shift it from the center with eccentricity of E. I'm gonna show you here a quick slide to remind you with what I was talking about. I'm gonna say this slide here. Here is P, and here's eccentricity E. So I can have it like this, just P and this eccentricity, or I can transfer this load, right, to the center. I'm gonna say now I have P and M, and this M is gonna be equal to P times E. It's the same thing. It's gonna be either this or that. Now, in this case, this triangular distribution, the resultant force of this needs to be aligned with this force. It has to be aligned with it, right? It has to be. Otherwise, the foot is going to be rotated. It's going to be unstable. This is why this distance from this point to this point is going to be x, and this is going to be 2x. Why? Because this reaction, it has to be in the CG of this triangular shape. And the CG is going to be at 1/3 from the base. So if you call this guy here from here to there, if you call this x, like in here, the total thing is going to be 3x. Now, I guess you know how to find out x. X is going to be equal to L/2 subtracting E, right? It's going to be right here. And the stress in this case, this reaction is going to be equal to P. Based on this, you can find out the stress. This is how the equation was developed.
Professor, in the formula, it says x times P. So it's P over x times B, and I'm guessing B is the base.
P is going to be this load. So
Right.
this P, yes.
And then the x.
X is going to be here.
Right, but the B, where does the B come from?
This B,
Mm-hmm.
the width of the footing in the other direction.
Oh, okay, got it.
You remember that in our definitions here, we said what is L and B?
Mm-hmm.
Footing length, footing width.
Got it,
So
thank you.
keep this in mind. Keep this in mind. Okay, let me draw here the footing for you. Here's the footing, right? L usually, definition of L, what is L? L is going to be the dimension of the footing parallel to the moment, same direction of the moment. This is going to be L. This has to be L. If the moment is acting this way, this is going to be L. And what is B? B is going to be perpendicular to the screen. It's going to be something like this, right? This is going to be your B. Also here, this is going to be your B width of the footing. Has to be. So let's say I give you a picture, I just rotated this. I made the footing like this, the moment is going to be acting the other direction, right? Now, which dimension that you're going to be calling L? It's going to be the one in the Y direction, right? It's going to be parallel to the moment. It's going to be the one resisting the moment, like the depth. Let's say when you have a concrete section, the depth is going to be the one in the same direction as the moment, resisting the moment. Okay. I have an example. It says here, following information covers examples 2 and 3. Here's the figure. They give you here the footing. The footing is 12 by 10 feet. Now, I guess you know now which one is going to be the 10 feet. It's going to be the one that's not resisting the moment. This one here is giving the same direction as the moment, right? This is going to be 12 feet. And here's the axial load P. It says the vertical load is 600 kips. This is service. This is good now because I'm doing here service design on the footing dimensions. I'm checking here the stress below the footing. 600 kips, while the surface moment is 720 kip/foot. So what do you want to do? Let's see here example 2. The example 2, it says the maximum soil pressure below the footing. When it says here maximum, is this maximum allowable or maximum demand? Like the actual pressure that happens below there.
Allowable.
Allowable?
Yes.
Can you come up with that level?
Yes, because what we do in foundation and footing, you told us that it's going to be on service load on ASD.
Okay. So what does it mean by allowable? Who's going to give you that level? Can you calculate that level? Or soil engineer is going to give it to you?
The soils report, right?
Yeah, it's going to be soils report. So actually this one's going to be the demand. What I'm asking you here is give you the demand, not that level. It's give you the maximum soil pressure. Give you the maximum actual soil pressure that happens with the footing based on this given loads. So these loads are demand, right? So when you have the demand here and then you take the dimensions, you find out the stresses give you demand. When you compare it to the limit, you would call the limit as that level. but I don't have here any limit. Just asking me, find out the stress below the footing. Okay? And give me here some options. I have example 3 that with some changes, but let me do first example 2. Example number 2. I have the loads 600 kips and M is going to be equal to 720. I have the length 12 and the width is going to be 10 feet. Now I guess we understand where's the width. It's going to be perpendicular to the screen. Contact area 120. Section modulus is going to be BL squared divided by 6. Just run the numbers, it's going to be 240 cubic feet. How about the stress due to the axle load? I have the equation for it, if you forget it. But this equation is simple. You just find out P divided by A. It's right here. It's going to be 5 KSF, right? Are you guys following? Yes?
Yes.
Okay, great. How about the stress due to moment? I'm going to be taking this moment divided by S that I just calculated out here. 720 divided by 240. Where's the 720 coming from? Say from here. Where's the 240 coming from for the S? Yeah, say S is
The
coming from
section
here.
modulus.
Yeah, I have 3 KSF. Now I'm lucky because F sub P is more than F sub M. So at one side, the stress is going to be equal to 8 KSF, right? You just add them. At the other side, you take 5, you subtract 3, it's going to be 2. This one here is going to be the stress at this location, right? It's going to be 2, and this one, the stress here is going to be equals to 8. So this is good. This equation actually is good. All of this analysis is good. Why? Because there is no uplift. There is full contact between the footing and the soil. So what is the maximum stress below the footing? I'm going to say here 8 KSF. Is this a demand or capacity? You say this is not a limit, this is not a level, this is a demand. This is the actual stress below the footing. You're good? Yes?
Could you repeat that last part one more time? So you by doing this analysis.
By doing this analysis,
Mhm.
I have taken the demand forces, axial load, and moment, correct?
Mhm.
I used the contact area of the footing to the soil, and I used the section modulus.
Right.
So with that, I have calculated the stresses below the footing, actual stresses. And this actual stresses means demand. They are not a capacity or a limit. The limit is the number that you don't want to go beyond. So for an example, if the soils report here says your maximum or the allowable pressure here is going to be equal to 7 KSF, is this a good footing? He says your max is 7. You cannot go beyond 7. Now you went to 8. You're going to say this footing is not good. This is not a good design. But if the soils report says 10 KSF is going to be the limit, it's going to be the allowable. I say, oh yeah, this is great.
Fine.
Yeah, I'm at 8. I still have up to 10. I should be fine. So what you're looking here at is the demand and not the capacity or the allowable or the limit. Okay. The example number 3, I'm going to be taking exactly the same footing. They say if the vertical load has been reduced to 240 kips, how about the moment? Moment is going to stay the same. No discussion here about the moment, means it's going to stay the same. So the moment is going to be 720, and guess what's going to happen? Load will drop down to 240. Now, also, he's talking about the maximum soil pressure. What's going to happen to it? Okay. Axial load is the same. Axial load dropped down to 240. Moment is the same, 720 foot. I guess same cross-section area or contact area and same section modulus. Nothing has changed, right? You see here anything changed? In problem 3, 3 from 2 is going to be only about the vertical load. So I said, okay, the only thing is this F sub P. It's going to change. It's going to be only 2 KSF. So I'm going to try. In one side, I'm going to say 2 plus 3. One side is going to be what? 5. And the other side is going to be minus 1. Now imagine this. Here's the footing. I'm trying to find out the stresses. So I said the stress here is going to be how much? 5. And the stress there is going to be how much? Negative 1. Are you guys following me or no? So in this case, it's going to be 2 plus 3 is going to be equal to 5 KSF. How about on this side? You're going to say in this side, you're going to say here 2 minus 3 is going to be minus 1 KSF. Not good, because the soil cannot take tension. I cannot consider this. So this equation, this treatment is wrong. I cannot do this. I'm going to be following here in case number 2. I'm going to go back here a few slides to show you what I'm talking about. I'm going to say, in this case, I need to use this line. It's going to happen in this situation, right? I need to find out all of that. So it's fine. Here is E, which is a moment divided by P. Which moment? This moment that didn't change, divided by the new axial vertical load. It's going to be 3 feet. This distance E is now 3 feet. I'm going to put this to be 3 feet. Total length of the footing, you guys remember total length was 12 feet. L over 2 is 6 feet, right? Yes, am I correct? Or I forgot the number. Is it 12 feet?
Yes, that's correct.
Okay, 12. So I have 6 feet minus 3 feet, x equals 3 feet. It's right here. Now let me use the equation. 2/3 P over X over B. You have all of these values, right? This is a constant. Your P now will become 240 kips. You have X is going to be 3 feet, and the width, what is the width? What is B? You see B is going to be this dimension, perpendicular to the screen. You can say 10 feet, you're going to have 5.33. So what's the conclusion? Conclusion is, when you reduce the amount of vertical load that acts on the footing, and you have only moment acting on it, or you have lots of moment compared to the axial load effect, you may end up with some lifting up of the footing, no contact. And guess what's going to happen to the pressure? If you remember when we did the quick analysis here, that was 5, that was what? -1. So what happened finally to the stress on this side? It becomes here 5.33. So this is not good. So when you have moment only on the footing, this is not good. You'd like to stabilize the footing by putting some vertical pressure on it. Otherwise, it's going to be just rotating like this. It's going to be flipping, right? It's not good. So using foundation, you'd like to have some good vertical load acting on it, especially when you have a moment. Make sense? Conclusion is clear or no?
Yes.
That was clear. Thank you.
Okay. I'm going to stop at this point. Next time, we're going to do here combined footings. It would be great if you start just to read about it to know what I'm talking about here. And let me know if you have any questions, or hang around and ask questions if you want to. You guys have a good night.
Professor.
Yes.
Do we have a submittal due this week?
Yeah, don't you?
Let me see. When's it due?
Sunday. Usually we make it Sunday.
Can we get more time on the submittal?
Why? What's happening?
It feels a little cramped, like just 3 days to do the submittal.
Yeah, I
When was the
agree. It is
submittal
really
posted?
I
cramped.
agree with that. Yeah.
Yeah, absolutely.
3 days
If
is not
someone's going to
enough.
say,
Plus,
let's
we have to
postpone it, everybody's
upload
going to
it.
say, yeah, why not? Right?
The thing is, we all talked about
No,
it on
professors,
Discord.
we have other classes too that
That's the thing.
it's hard to like do every assignment in 3 days.
Okay.
If it were due a
Which
Tuesday
submittal
right
is
before
due?
class, would have been a lot
What
better.
submittal is due? Number 3.
Yeah.
Column, spiral column. All right, you have 2 options. First option is to have it like middle of the week, give you a couple of days. I have another option, because I'm going to have a new submittal. I'm going to be posting here today by end of today, so we can combine them both, not for this coming Sunday, for the following Sunday. Which one do you guys prefer?
So you're saying one option is take 2 submittals basically and push it till next week, or keep the same submittal till sometime middle of this week?
Yeah, like Tuesday or Wednesday or whatever, something like that.
What day would the first option be?
Let's say Wednesday is good.
I like that option.
So what do you guys think?
Yes.
Yeah, that
Wednesday
option
sounds good
sounds
too.
good.
Wednesday, or keep both of them to the end?
I think
Like-
the Wednesday one.
I think Wednesday is a pretty good idea.
Wednesday.
Yeah, we also have time to go to office hours on Tuesday, if we come across anything.
Okay, all right. I'll change
And
it.
then what about to the next submittals? Is it going to be, for example, from Wednesday next week to Sunday?
The other submittal, let me tell you the date. So for example, this submittal, instead of having it on the 1st, is going to be on the 4th, right?
Mhm.
And the following one is going to be in the 8th.
So the next one will also be on a Wednesday instead of a Sunday.
No, it's going to be also on Sunday. It's going to be on the 8th. This one, I'm just extending for you guys. But the next one is not going to be extended. The next one is going to be on Sunday, and you
So the
have
next
plenty
one
of
is going to
time.
be normal, right? Like,
Yeah, yeah.
Okay, roger that.
But are you going to post it today?
Yes, I'll post it today. And you can start work on it today. And if you are able to finish it by this Sunday, both of them, if some of you have time, by all means, go ahead and submit it.
So one on the 4th and one on the 8th.
Yes.
And the one due on the 8th will also be posted today.
Yes.
Okay, okay.
Can't they all from now on all be due on a Wednesday instead of Sunday?
Actually, I have received the request from a few people that say we prefer it to be Sunday.
I prefer it to be
So
Wednesday.
I used to ask for it to be Wednesday, if you guys recall, and then a few guys said, give us the weekend.
It's very short, and plus we can't even ask you a question if we get confused when
Okay.
we do the
All
Yeah,
right.
exactly. It's better if it's due
Okay,
Wednesday, so you have your office hours.
let's do it this way. I don't want it to be in the middle of the week for some of you guys, unless everybody agrees. Is everybody agree? If someone's gonna say no, we prefer it Sunday, I'm not gonna do it Sunday again.
I think it's more about the amount of days more than the day it's due. I think it's more about like how many days is given to complete the assignment.
Okay. So if
Like,
this one here, I'm gonna push it because this one I guess was posted like 2-3 days ago. This submittal here, the submittal which is due this coming Sunday, it was posted 2-3 days.
28th. It was posted on
I only
the
saw it was yesterday.
Yeah.
Yesterday? Okay. So let's say 28th, and I'm asking for it on the 1st. So let's say I'm gonna do it here for the 4th, okay? The following one is gonna be on the 8th. I'm gonna post it tonight. So you're gonna
That's
have
fine.
now, we have plenty of time to it. Does it make sense?
Yeah, that's fine.
That works for me.
Do you want it to make it Sunday, or do you want to also make it Wednesday? But if I'm gonna make it Wednesday once, I'm not gonna change it. Everything is gonna be Wednesdays.
Yeah, I think Wednesday is better.
Are you guys sure?
For me, it works
Yes.
better for the weekend, but I
Okay,
like that
so I'm
for this
not-
week.
Great.
For this
Okay,
week,
I'm gonna
it
make it
works well.
Wednesdays. I'm not gonna change it anymore. I'm gonna keep it Wednesdays.
Yes,
Right?
I like that.
Okay.
For submittal 3 and 4, we're gonna go 4th November and 8th November. This is correct, huh?
No. One of them is gonna be 4th, and the other one's gonna be 11th.
Okay.
Yeah, that's right.
So everything's gonna be now Wednesdays.
That-
Don't expect anything for Sundays.
Perfect.
And there's no extension anymore. I mean, we're done with it, right?
Fair
Yeah.
enough. That's good.
Okay.
Yes.
Thank you.
All right.
Thank you.
And one more thing, can we get some feedbacks from the previous submittals to see if we are in the right track or wrong, please?
Okay, so the best way, because even for your midterm, I expected that you guys will communicate with me, try to review it, but only a few of you guys have done it. So what I would like to do, I'm just gonna get you here the kind of quick solution to it and review it with you. But I cannot grade everybody's and discuss it with him like in the office hour. We have more than 40 people, and we didn't even yet finish discussing the midterm with you guys in person. But I'll give you some feedback. I'm gonna tell you exactly what to expect out of this.
Yeah, that helps because I think the main point is to learn actually the
I
subject.
have no problem. Absolutely.
Okay, thank you.
All right, good night.
And what about the all grades in exams or the fifth?
Okay, this means that you did not communicate with me and you did
I
not.
did
open up-
actually.
So did you see your grade?
You just told me my grade. I didn't
You have seen it on the screen. Did we go through your solution?
Yes.
Okay, good. All right, so you know about it. Good. I'm looking for the rest of the people. I need the rest of the people to approach me and discuss their midterm.
You want that done during office hours or by email or?
Office hour, or you can hang around. After this, go ahead and join the office hour meeting. In 5 minutes, I'm gonna start the time.
Okay.
Professor, can you pull up the midterm right now?
What do you mean? For you?
Yeah, I just want to see.
So you want everybody to see it?
No, not the just like the questions.
Okay. Why don't you see me in the office hour? And
Okay.
it's gonna be 1 by 1. So please, if you find yourself in the waiting room, just wait. Maybe someone else is there. Okay.